A cache is a small, very fast memory that sits between the CPU and the big, slow main memory. Think of it like a desk drawer that holds the tools you use most often while the whole toolbox is in the garage. Modern computers use several levels of cache: L1, L2, L3. L1 is the smallest and fastest, located right on the CPU core. L2 is larger but a little slower. L3 is shared among cores and is larger still. By keeping frequently needed data close to the CPU, the cache cuts down the time the processor spends waiting, improving overall speed. If the CPU could reach main memory for each instruction, the program would run much slower, because memory access can be 10 to 100 times slower than a cache access. Every memory address is a binary number. To decide where a block belongs in the cache, we split this address into 3 parts. Tag identifies which block of main memory is stored in a particular cache line. Index tells which cache set or line to look at. Block offset points to the exact byte or word inside the block. For example, with a 32-bit address, a cache line size of 64 bytes, 2 to the 6, and 256 cache lines, 2 to the 8, we need 6 bits for the offset, 8 bits for the index, and the remaining 18 bits become the tag. The address 0B0 10 10 11 1100 110 101 10 10 11 11 would be broken into. Tag equals 0B0 10 10 11 1101, 18 bits. Index equals 0B10 1 10 1, 8 bits. Offset equals 0B1 10 10 11 11, 6 bits. This partition lets the hardware quickly find the right place in the cache. In a direct mapped cache, each memory block can go to exactly one cache line, like a set of numbered mailboxes where each letter has a fixed slot. The placement rule is cache line number equals block address modulo number of lines. When the CPU requests an address, the hardware extracts the index to select a line and reads the stored tag. If the stored tag equals the address tag, we have a hit. Otherwise, it is a miss and the line is replaced. Numerical example. Cache size equals 8 kilobytes. Line size equals 64 bytes. So 8 kilobytes divided by 64 bytes equals 128 lines. Number of bits for offset equals log base 2 of 64 equals 6. Index equals log base 2 of 128 equals 7. Tag equals the remaining bits. Assume a 32-bit address 0x0, a 3C5F28, binary 0010010100101111100010001000. Offset equals lower 6 bits, which is binary 101000 hex 0x28. Index equals next 7 bits, which is binary 111110 decimal 124. Tag equals the remaining 19 bits, which is binary 000010111110000101. The cache line 124 is examined. If its stored tag matches the computed tag, the CPU gets the data in one fast cycle, a hit. If not, the CPU must fetch the block from main memory, a miss, and write it into line 124, updating the tag. The direct mapped method is simple and cheap, but 2 blocks that map to the same line will constantly replace each other, a problem called conflict miss. A fully associative cache lets a block be stored in any line, like a parking lot where a car can park in any empty spot. To find a block, the hardware must compare the address tag with the tag of every line simultaneously. This is done with a set of comparators or a content addressable memory, abbreviated CAM. Replacement policies decide which line to evict when the cache is full. Common policies are as follows. Least recently used, abbreviated LRU. Evict the line that has not been used for the longest time. Random, pick any line at randoms. FIFO, first in, first out. Numerical example. Cache size equals 4 kilobytes, line size equals 64 bytes, which gives 64 lines, fully associative. Tag bits equals 32 minus 6, offset equals 26 bits, no index. Assume the cache currently holds tags 0x12b3, 0x4c5d6, 0x7e8f9, and so on. The CPU requests an address with tag 0x4c5d6. All 64 tags are compared in parallel. A match is found, hit. If the request tag were 0xabc01, no match occurs, miss. The miss penalty forces the controller to fetch the new block and place it in a line chosen by the replacement policy, for example the LRU line. Fully associative caches have the lowest conflict miss rate but need many comparators, making them larger and slower for big caches. Set associative mapping is a hybrid. The cache is divided into several sets, each containing a few ways. It combines the simple index of direct mapped caches with the flexibility of associativity. Think of a library where each shelf is set holds a few books, which are ways. A book's call number decides which shelf it belongs to, but any spot on that shelf can hold the book. If the cache has S sets and W ways, total lines equals S times W. The address is split as offset log base 2 block size, set index log base 2s, tag remaining bits, illustrative calculation, cache equals 16 kilobytes, block equals 64 bytes becomes 256 lines. Four-way set associative becomes 256 divided by 4 equals 64 sets. Offset bits equals 6, set index bits equal log base 264 equals 6, tag bits equal 32 minus 12 equals 20. Address 0x3f2 a 1c4d. Offset equals lower 6 bits equals binary 110101, which is 0x35. Set index equals next 6 bits equals binary 011100, which is 28 decimal. Tag equals upper 20 bits equals binary 0011111000101010, which is 0x3f2a. Set 28 has 4 ways. The hardware compares the incoming tag with the 4 stored tags in that set. If any match, it is a hit. Otherwise, it is a miss, and a replacement policy, often least recently used, chooses which of the 4 ways to replace. Set associative caches strike a balance. They reduce conflict misses compared to direct mapped caches while using far fewer comparators than a fully associative cache. Hit ratio H equals number of cache hits divided by total memory accesses. Miss rate M equals 1 minus H. Miss penalty P equals extra time to fetch a block from the next memory level, for example, main memory latency. Average memory access time, a MAT, equals hit time plus miss rate times miss penalty. Sample data. Assume hit time equals 1 nanosecond, time to read from L1. Miss penalty equals 100 nanoseconds, time to get data from L2 or main memory. Out of 1,000 accesses, 950 are hits. Calculations. H equals 950 divided by 1,000 equals 0.95, 95%. M equals 1 minus 0.95 equals 0.05, 5%. AMAT equals 1 nanosecond plus 0.05 times 100 nanoseconds equals 1 nanosecond plus 5 nanoseconds equals 6 nanoseconds. If we improve the hit ratio to 98%, AMAT becomes 1 nanosecond plus 0.02 times 100 nanoseconds equals 3 nanoseconds. Showing how a small increase in hit ratio dramatically reduces average access time. These numbers help architects decide how large a cache should be and which mapping technique to use. When building a cache, hardware engineers must store the tag for each line and compare it with the incoming address tag. Tag storage : each line needs a tag register, often implemented with SRAM cells. The width of the tag is the total address bits minus offset and index bits. Comparators : direct mapped caches need only one comparator per line, just an equality check. Fully associative caches need a comparator for every line in parallel, which can be expensive in area and power. CAM, content addressable memory, a special type of memory that returns the address of a matching tag in one cycle. CAMs are fast but consume a lot of power and silicon area, so they are usually used only for small, high-performance caches, for example translation look-aside buffers. SRAM versus CAM trade-off. SRAM cells are simple and low power but require external logic to compare tags. CAM provides built-in comparison at the cost of higher power and larger cell size. Designers often implement set associative caches with a small number of SRAM-based ways plus a modest comparator tree achieving a good compromise. Other considerations include write policies, write-through versus write-back, write allocation strategies, and replacement policy hardware, for example counters for least recently used. All affect speed, complexity, and energy consumption. Explanation: choosing a cache mapping technique depends on the workload and design constraints. Workload pattern: if the program accesses many different blocks that map to the same line, high conflict, a fully associative or higher associativity set associative cache reduces misses. For workloads with good spatial locality and few conflicts, a simple direct mapped cache may be sufficient. Cost and area: direct mapped caches need the fewest comparators and tag storage, making them cheapest. Fully associative caches grow quickly in area and power. They are usually limited to small sizes, for example, TLB's L0 caches. Latency requirements: direct mapped caches can often be accessed in one clock cycle because only one tag is checked. Set associative caches add a small penalty, usually 1 to 2 cycles due to multiple tag comparisons. Fully associative caches may need extra cycles or more complex pipelines. Power budget: more comparators lead to more switching and higher power. Battery-powered devices such as smartphones and IoT often prefer lower associativity caches. Scalability: as cache size grows, associativity is increased to keep miss rate low, but designers must balance the rising hardware cost. Guidelines summary: Step 1. Start with a direct mapped design for small, low-power caches. Step 2. If simulations show greater than 10% conflict miss rate, move to 2-way or 4-way set associative. Step 3. For critical high-performance cores, for example superscalar CPUs, use 8-way or higher set associative L1 or L2 caches. Step 4. Reserve fully associative caches for very small latency-critical structures, such as TLB or L0. By matching the mapping technique to the application's memory access characteristics and the system's cost or energy limits, designers achieve the best trade-off between speed and complexity.